Voila. And then she tells me if I do a Command F, it gets big. That's exactly what I wanted to see. Okay, I'm going to show you the movie. We're going to start out here in 1979. What you're looking at is several things, obviously. One, you're looking at the observing system that we had in 1979. Those are the stations we were able to use that could measure long-term trends in carbon dioxide. There's not very many of them. There's 5 that are gray. Those are called background conditions. Those sites, because of their location and the wind direction, all that, capture air that has been across the ocean for a long time or isolated from human activity, so that you're getting something that represents a sort of an average for that latitude, longitude, etc. The red one is Mauna Loa, and the blue one is South Pole. These are representative of the 2 hemispheres. And then that light gray one is Niwot Ridge, Colorado. It's there for convenience because we're located in Boulder, Colorado, but it's high altitude, gets us some free tropospheric air, but it does pick up a little bit of air from Denver every now and then, and you see that in the record. So we're saying that that's locally influenced on occasion. What you see over here is a latitudinal gradient going from south to 90 degrees north. You see South Pole down here, Mauna Loa here, and then there's your background stations and your locally influenced station. So we're going to watch those as we go forward. We've got a clock here, and over here you're going to get a trace of Mauna Loa. It's going to show you the CO2 curve as it evolves, starting in 1979, and we'll start going back in time after that. Then it's from that point forward. Oh yeah, the South Pole continues to go up as well. So we're going to follow this a little bit. I'm going to make a few stops and try to make a couple of points that we have learned as a result of making these measurements that were very important. So I should be able to hit the click, right? To make it go and push that. Yes. Okay, so now as you see this, if you watch the months here, it's January, July, October. Let's go back to July and see if we can stop it. Okay, a little further. Right there. Okay, we're getting into the summer. The northern hemisphere has plants. Most of the biosphere is in the northern hemisphere. Draw the equator through that line, you'll see most of the land is up there. And that's where your terrestrial plants are all growing. In the southern hemisphere, Australia is a desert, Antarctica is a desert, the lower part of South America is a desert, so you're not getting much. About 90 to 95%, I think the latest estimate was 92% of the terrestrial biology is in the northern hemisphere. So you're going to see that really kind of driving these swings. And in fact, you can see that here, because you get this oscillation that's 10 times bigger than the oscillation at South Pole. That also tells you that the biosphere is located mostly in the northern hemisphere. So let's let it run again. I think I have to hit the click. Yeah. Now you see that everything is going up because CO2 is going up in the atmosphere. Note how South Pole sort of captures the global trend without a whole lot of oscillation, and that's how it shows up over here. The background stations don't wiggle as much as some of these light stations. But we're getting at a point where I want to kind of put a halt to this right about here. Yes. What you're looking at is 1990. You can see we've got a fairly well-developed network now. We're able to monitor CO2 at all of these sites and get a very robust number. When we say the global average of CO2, we know that number to 1 part in 4,000. So there's really no question about that, and it's highly accurate. You can see a few of these little local sites there. We're trying to understand how the terrestrial environment influences the CO2. But another thing happened from these data. When we looked at the gradient of CO2 from here to here, and we looked at the gradient of another compound, it's called C13 CO2. In other words, it's an isotope of carbon that's locked into the carbon dioxide molecule, and it's supposed to show a certain trend. When you look at both of those, and you looked at the growth rates, you couldn't explain it based on what we knew about the Earth system. It turns out there was a huge unidentified terrestrial sink for CO2. As we went further in this to study it and learn about it, we found out that, lo and behold, maybe it looks like about 1/3 of the CO2 emitted through automobile tailpipes, power plants, etc., in the United States can be accounted for by uptake, long-term uptake, in the North American continent. Now, politicians were very interested in this, right? Because if there came to any negotiations, they would say, well, gee, we're only emitting 2/3 of what you say we're emitting because we're taking it up over here with the land. But that was not our reason to continue with this. Our reason to continue was to try to understand the system a little bit better. So that was a big find, and it took that network to do it. You can't do it with 1 or 2 measurements, a little bit here and there, high calibrations, very high quality stuff. So as it goes forward, you can see the trace continuing. There's your southern hemisphere, it's off a little bit from the northern hemisphere, right? That's because summer is in January and winter is in December. So you're going to catch it, it should be exactly opposite, and that's exactly what it is. Notice what happened after 1990 here. Look how many local sites there are now. We've got a lot of partners out there collecting flasks for us, shipping them out so that we can analyze these and understand what's happening on the terrestrial environment. And we're getting a better and better handle on that. It turns out that half of the CO2 emitted into the atmosphere is either taken up by the ocean or taken up by plants on the land. We don't know the exact split. You hear different estimates, 50-50, I've heard 70-30 and 30-70. But the bottom line is we do know that half goes into the ocean and land and doesn't come back again, at least not in the near term. That's big. And notice the variability on some of these local sites. If you get close to a source, you're going to get a lot of CO2. We don't use those to compute global averages. They're just too locally influenced and too variable. We do use them to understand how the plants are breathing in and breathing out and taking it all. You also will see them go a lot lower because if they're near a forest, they're going to suck up more CO2 out of the atmosphere right nearby, and you get that. When you're taking your average, and we're just using these marine boundary layer sites, these gray ones, we have a good picture of what the global average is doing. Okay, now going forward, I'm going to let this run a bit. You'll see more sites go in and the Mauna Loa curve go forward. And then we're going to reach a point where these graphics is going to change because we got to go back a while. We want to look at it and see what was this all during human civilization. So what if CO2 is making it to 400 parts per million? And you can see that they'll reach, in the wintertime, it'll reach the higher value, and then it goes back down again. Every year, plants are making leaves and trunks and stuff in the spring and summer, and they are emitting the CO2 as they decay. Drop your leaves, they all decay, and you have CO2 going back into the atmosphere. Now look at all of the local sites that have gone in, because it's really a tough question that everybody's working on. We still don't understand it as well as we would like to, but it's a very robust number. It's not going to change one way or the other in the near term. So this is what we're going to do now. This is Dave Keeling's record, and Dave was the guy who started this whole thing. By 1957, he said, you know, I'm going to pause it at the end of his record here. Should be right about there. Okay. Dave had a hard time convincing people that he could provide the calibration scale and standards and make some measurements of something that was parts per million in the atmosphere at very, very precise levels, 1 part in 4,000. And he said, I need to do this in places like Mauna Loa and South Pole so I can have a picture of what the world is doing overall. So it was a bit of genius on his part. He didn't expect to see what he saw. He didn't expect to see the seasonal cycles. He didn't expect to see the trend go up like it was going. So he learned a lot from that, and so did the world, and we've gone forward. Now what's going to happen next, and I hope I can stop it in time, is we're going to zip back a little bit, maybe go back a couple hundred years, and we'll discuss where that is, because I want you to understand the impact of human development on this cycle. We have a huge influence on this planet, and if you have a doubt about that, you can look at how many aircraft take off every day. You can look at those night lights pictures that are often put out by National Geographic, or you can look at the CO2 record and see what it's doing. So I'm going to drive it forward a little bit. Anybody have questions? All right. Go, baby, go. Okay, it's going to take a second here, and then it's going to jump on me. There we go. Perfect. Okay, now what you're looking at, notice there's two more sites here. There's one here at Law Dome, offshore of Australia, and there's the other one here at Cycle Dome. These are coastal Antarctic sites with rapid snow buildup, and so you can go back in a recent time, maybe not hundreds of thousands of years, but a few thousand years before you reach the bottom. Basically, you drill in and you take a piece of ice, you grind up the ice, and you measure the CO2 that's in the bubbles in the ice. Our colleagues at Australia started this mess, and they did a great job. These orange lines here are from the Law Dome site. You can see how they line up beautifully with the Mauna Loa record. So there's no bias, there's no issue with sampling problems and things like that. We have a nice, smooth record going from recent time, going back about the beginning of the Industrial Revolution, which is around 1750, 1800 or so. There's a couple of things to notice here. No, Cycle Dome, by the way, they've got fewer samples, but they show the same thing. So again, there's no bias brought in by the site we chose, etc. But this was really, really telling. Because we think of the Industrial Revolution, that was the 1800s, and first thought comes to mind is England with smokestacks spewing out smoke, and all over Europe this was happening, and the air was bad and everything. Well, from 1800, right here, to 1900, CO2 went up 10 parts per million, over 100 years. From 1900 to 2000, it went up 100 parts per million, 10 times faster. That is incredible when you think about that impact on the planet, because CO2 is a greenhouse gas. It's an important greenhouse gas. We wouldn't have life on this planet as we know it without CO2 in the atmosphere. It helps keep the planet from freezing. So, looking at this, and by the way, we haven't straightened out any lines. These have all the wiggles that you looked at before. The red and the blue and the green all have all the wiggles that you've seen before. So hang on to those because they're going to get a little tighter. Now we'll go back a little bit further, and we'll stop right about here. We see something a little strange, a little dip in the CO2 record. Anybody have an idea what that is? Little Ice Age, right? I heard somebody say it. It's the Little Ice Age. This is Shakespeare was busy writing, and several others. They like to stay inside. We had coffee houses, so you can stay inside where it's warm, fomenting revolution and creating things like democracy and all of that. All of that was happening during the Little Ice Age, and it was cold in Europe. It was miserable. But interestingly, note that CO2 went down too. So this says something about temperature and carbon dioxide. If you raise carbon dioxide, it's like putting a blanket on your bed. You're going to get warmer. But if you raise the temperature, it puts another blanket on your bed. It adds CO2. And this is something that confuses people at times. We're going to look a little more back into the record, and you can see how that happens. They have this sort of a game that they play. So if you don't stop one or the other, you're going to continue going, and you're going to keep going faster and faster. So there's a little ice age, and we'll go back a little bit further and try now. Let's do a little history lesson for everybody. We'll go back right about here. This period here is warmer. There's more CO2. There's more CO2 in this thing, and that's called the middle warm period. For 500 years, roughly between here and here, there was a civilization in Greenland. They had ships going in and out, farms, and all kinds of things along the coast of Greenland. It was big. So again, a small shift in CO2 associated with a significant shift in temperature. Okay, we're going to go back a little further. I notice the left graph is disappearing on you, so take a close look. From looking at these numbers, we can say the pre-industrial CO2 is about 270 parts per million. And yes, sir?
Could you just explain again why increased temperature leads to more CO2?
Yes, yes. It increases respiration on the planet. If you get warm, you breathe faster. Plants do the same thing. And soils respire more rapidly. So they're putting more CO2. So if you raise the mean temperature, you're going to kind of kick that up and put more into the atmosphere. It's
Plants don't take the CO2 out of the atmosphere?
they do that seasonally. Every season, every spring they're taking it out, and every winter they're putting it back because they're dropping their leaves and the leaves are decaying. Or the trees are falling over and the trunks are decaying, and all of those things go forward. So it's this cycle of carbon that's constantly going on among the biology on the planet. I mean, some of this gets washed into the ocean and it goes through marine cycles as well. That's more of a long-term thing. But yeah, the plants, if you just raise the mean temperature, you're going to have more respiration. You're going to get higher numbers over here. But notice this. We're about year 0 down here. Jesus was born, Roman Empire, Greeks were kind of starting in their decline. There was a lot going on. All of Western civilization, every bit of Western civilization was what? 280 parts per million, plus or minus about 5, 2, not much. So this is significant. This is a period in history where human civilization actually could survive and develop and evolve. Let's go a little further. And this is going to disappear on you there. And now we're going to go to another ice core from a different part of the planet. I'm going to go a little further here. Okay. This is the Vostok Ice Core, and we have that up here. The Vostok Ice Core runs from, it's in Antarctica. It's a Russian station. There was a big core down there, but that's a low deposition area, so you can go back very far in time with these samples. You just get a wide time interval between each sample. But you can see it matches up pretty well with this, as far as we can tell. But this is the bottom. This is the last ice age down here. CO2 at the last ice age was around 180 parts per million. Throughout most of human civilization, which goes back to where? The Egyptians 5,000 years ago, that'd be 3,000 BC. The Chinese, maybe a few thousand more, 5,000. Let's push it, say 10,000. It really doesn't matter. You're looking at 270, 280 parts per million carbon dioxide in the atmosphere during the entirety of human civilization, allowing us to have temperatures such that we could have agriculture, create cities, make inventions, invent the wheel, etc. Do all these things that we needed to propel society forward. I'll go a little further now. Take a look at this ice age. Hello, maybe. Here we go. Now, this is a 20 here, in case you can't see it. How long did it take CO2 to rise from 180 to 280 parts per million? 15 to 20,000 years. 100 parts per million, natural cycle, 15 to 20,000 years. We did it in the 20th century in how much time? 100 years. This is scary when you start to think about it. It's 150 to 200 times faster than we've seen since the last ice age and even before, which I'm going to show you. Now there is a curiosity. It's still in the ice age, but it's going to swing back again, and we can talk about that too, because it's a good example of temperature and CO2 influences. Okay, what you're looking at here, the ice age, we also call them glacials. There's another glacial. This is an interglacial, and this is an interglacial. Carbon dioxide is around 280 here. It's around 270, 280 here. Where was human civilization? Wasn't there. We don't have any evidence of it. It might have been, but even 100,000 years ago, we should probably be able to detect some resemblance of that. I mean, Rome was 2,000. We see lots of Roman ruins. Egypt goes back a little further. We should see something somewhere in the world. We see nothing. So here it was, ripe for agriculture, development, etc. This would have been Homo erectus, not Homo sapiens at that point, probably, but nevertheless, we just weren't quite there for that. I might miss that on the anthropology. I'm not an anthropologist. But the point is that there were the conditions right there, just perfect, interglacial, 100,000 years ago. We didn't have civilization. This is a jewel. What we've got now is a jewel. Science, art, literature, everything we do. Let's go further. Now you see another interglacial and a glacial. Now the ice core record gets a little messy here because the integrity of the ice is not so good as you go further and further back in time. And there's shifting even beneath the continent in these big sheets. There's shifting and mixing up, and it's also hard to sample sometimes. So the basic idea is there. It's just not as clean as the recent years. The interesting thing about these cycles are called Malinkovic cycles, and they're named after a fellow who described them in terms of the wobble in Earth's orbit, which is caused by orbits of Jupiter and Mars. So we won't go into that too much. But the point is, that is a driver that drives temperature first and CO2 second. So the thing that stopped CO2 from going up here is that you kind of went to the next phase of the Malinkovic cycle, because you had that play off of each other all the way up and down again. By the way, down here, the geologists are all telling us that the temperature is about 4 or 5 degrees colder than today, Celsius. 4 to 5 degrees Celsius. We're anticipating that doubling CO2 will take it 2 degrees Celsius. What it means is that part of that is due to the increased insolation and part of it is due to the carbon dioxide. So it does help us filter those things out. Going further, another interglacial every 100,000 years. It's like clockwork, which is what it is. So this is the record as far back as we can go with measurements of carbon dioxide. There's other ways to go back millions of years by going into proxies like barium and that. But this is the CO2 record. Note, this 10,000 or 10 to 20,000 years here is a straight line. But on 100 years, and that's still got the wiggles in it, it's incredible. So what we've done is a huge experiment. And when we look back at this and think, well, 180, 280, 380, if you will, 100, 100, 100, 4 degrees colder here. Here it is, and we anticipate it's going to be a couple degrees Celsius warmer. Well, what is 2 degrees Celsius? 2 degrees Celsius is roughly 4 degrees Fahrenheit. 4 degrees Fahrenheit over the entire globe average. Most of that's going to be over the continents because the oceans will be more or less very small change over the oceans. So you got to multiply that by 3, in other words 12 degrees over the continents average. In some places on the continents will get warmer. What if it's more than 2 degrees Celsius? How hot's it going to get? How's our agriculture going to be? What's that going to do to immigration? What's that going to do to poverty? What's this going to do to opportunities to make money? I mean, there's a lot of things happening here. But it's change. And we need to be prepared for change. We need to be willing to adapt to change. And we need to be able to try to deal with those aspects of change we don't like. Those are all tough decisions for society. I'm going to try to slip out of this if I can. Hit escape. So, is there any questions while this is up? Because I can go back and forth. I can take this, I think, and make it go back by being a good boy. Whoop. Go right here. There we go. So if you want to go back and look at, hello.
Play again.
Oh yeah. Now you got to stop it, right? Oh, Macintosh. Okay. Okay. So we can stop anywhere we want and take a look at things. If somebody has a question, did I confuse everybody into silence? What do we have?
Besides the ice cores, is there any sort of like other chemical testing that you can do, say like volcanic rock or any other things that are being used to date even further back to see if this point's ever been reached in the past?
The question was, can we go back further by looking at volcanic rocks and sediments and things like that in the ocean, et cetera? And yeah, the answer is yes, and people are doing that. And like I said, they're looking at proxies like barium and other isotopes to try to understand what it was. We do know about 3 million years ago, CO2 was very high on the planet, but it's a very different planet. And then if we go back to the Paleocene, Eocene boundary back around 60-some odd million years ago, it was pretty warm then too. But right before that, there were dinosaurs all over the place, and Denver was a marsh. So it is a different planet when those things happen. And human civilization has been at this 280 plus or minus 10. And that's where we are. Don't see a big change. Yes, sir?
Yeah, you're talking about industrial revolution, and then this and the coincides with the deforestation that would have taken place in order to supply the industrial revolution. The replanting, of course, has been taking place the last 30 years. Has that had an effect?
I'm not sure on the question again.
Oh, the deforestation and the replanting of the forests.
Oh, forests. Oh, yes, yes. Well, one of the things that the United States did in the 1800s and Europe was get very busy deforesting the continents. We took down a lot of forest to put in farms, so you lose the longer-term storage. Forests do, not only does the carbon go into the tree trunks, but it goes into the soils, and that's where the long-term storage is. We don't quite understand how fast or how well that works. Certain aspects of agriculture do that, and other parts don't. So it kind of depends how we're working this. Like I say, we don't understand it. Going back in time, I don't think that's the real driver of the big changes we're seeing. Although when you go to an ice age, you have a lot fewer forests there to take up CO2 or to release it or even respire. So how that would play out either way is hard to say.